In this video, the following concepts are studied: scientific notation, accuracy, precision, uncertainty, resolution, significant figures. Scientific notation. Sometimes in scientific problems, we encounter very large, or very small numbers. We give a real example of very small numbers. We know that all matter is made up of atoms. The atom has a nucleus. Inside the nucleus there are protons and neutrons. The radius of the proton is approximately equal to this number. Writing this number and reading it is not easy, but it can be easily displayed with a scientific notation. As an example of large numbers, consider the distance from the Earth to the Sun. This distance is equal to 15 trillion meters. It is not easy to write and read this number, but the scientific notation makes our work easier. The scientific notation consists of two parts. The first part is a number between 1 and 10. The second part is a power of 10.
Please see all the examples to learn the method completely. A new point has been made in each example. We divided the examples into two parts. The first three examples are for numbers greater than 1. You can see that in these examples the decimal point has to move to the left to be just one digit ahead of it. But the following examples are numbers smaller than 1, so the decimal point must move to the right with only one digit before it. If the decimal point moves to the right, the power of 10 is written negatively. If the decimal point moves to the left, the power of 10 is written positively.
Example 1. Consider the following number: 5,000. First you need to know that to the right of this number can be placed decimal point. Because we move to the left, we write positively. Equals 5 times 10 to the power of 3. Attention! In mathematics, 5.000 equals 5. But this is not the case in physics. We examine this issue in the section on measurement accuracy and errors.
Example 2. Consider the following number. To the right of this number, we put the decimal point. Because we move to the left, we write positively. So the power of 10 becomes 5. Equals 4.28 multiplied by 10 to the power of 5.
Example 3. What should we do if the number itself already has power? Consider the following number. Decimal point must move to the left, to be just one digit before the decimal point. Because 5 digits move to the left, we add 5 to the power.
Example 4. What should we do for numbers smaller than 1? Consider the following number. We have to move the decimal point to the right, to be just one digit before the decimal point. As we move to the right, we write the power of 10 as a negative number. That is, -6. Therefore we have
Example 5. What if there is 0 between the digits of a number? Consider the following number. We have to move the decimal point to the right, to be just one digit before the decimal point. As we move to the right, we write the power of 10 as a negative number. That is -5. Therefore we have
Example 6. What should we do if the number itself already has power? Consider the following number. We have to move the decimal point 3 digits to the right, to be just one digit before the decimal point. So it becomes -3.
Measurement is one of the main tasks of various sciences, especially physics. There are two basic concepts in measurement that may be confused: accuracy and precision. Accuracy indicates how close the values are to the correct value. Precision shows how close the values are to each other. Suppose 4 people shoot at a target. We want to check the results. Pay attention to the first-person bullets. They are all close together, so it has a high precision. Every bullet is close to the target, so accuracy is also high. Second person. All bullets are close together, so it has a high precision. But the bullets are far from the target, so the accuracy is low. Third person. The bullets are not close to each other and are far apart, so the precision is low. But the bullets, although they are far apart, are scattered around the target, meaning that they are close to the target on average, so the accuracy is also high. Fourth person. The bullets are not close to each other and are far apart, so the precision is low. But the bullets are far from the target, on average they are close to another point, so the accuracy is also low. Seeing 4 results at the same time helps to learn more.
Significant figures or significant digits, digits in the number that are necessary to indicate one quantity. Suppose we want to measure the length of a box with a ruler calibrated in centimeters. Starting from 0, we see that we reach the number 8. In fact, the length of the box is more than 8 centimeters and less than 9 centimeters. So we can definitely say it is 8 centimeters. And for the extra part, we have to guess, for example, say 0.2 or 0.3. This shows that we cannot comment with certainty, but there is an uncertainty. This figure is called uncertain or estimated. Now consider another ruler that is graded in millimeters. We see that we can express the digits of 8 centimeters and 0.2 centimeters with certainty, but another additional part remains. We have to guess again, for example, say 0.06 centimeters or 0.05, this figure is again a guess. That means we can write a total of 8.26 centimeters. The sum of the number of certain digits and estimated digits represents the significant figures. For example, in the previous measurement, when we obtained the number 8.26, we have 3 significant digits. If we report the number 8.26 with the first ruler, We gave wrong information. But the second ruler can measure this number. What is the difference? The answer is in resolution of the tool.
Resolution is the smallest amount that a device can measure. For example, the first ruler can measure 1 centimeter, and cannot measure less than this amount. So its resolution is 1 centimeter. With this tool we can report a number like 5.8 centimeters, where 8 is a estimated number cannot measured by that device. The second ruler can measure 0.1 centimeters, so its resolution is 0.1 centimeters, and cannot measure less than this amount. With this tool we can report a number like 5.87 centimeters, where 7 is a estimated number. Suppose that with each of these rulers measured and this number reported, some meaningless and meaningful numbers are reported. With the first ruler, this part is meaningless. And with the second ruler, this part is meaningless. Important note, if we have a number, we will start from the left to find the number of significant digits, and count from the first non-zero digit to reach the last digit of that number. Note that we do not consider 0 before the non-zero digit, but we must consider 0 after non-zero digit. Example. This number has 5 significant digits. This number has 2 significant digits. This number has 4 significant digits. It is better to write the number as a scientific notation, so that we do not make mistakes in. This two number both have 2 significant digits. You can see that the power of 10 has no effect on the number of significant digits.